So dear students, so we'll have our part 5 of chapter 1. Here we'll be discussing 1.12 to 1.14 of your NCERT. The contents of this presentation are dipole in a uniform external field. There we'll define an important term, that is torque. Dipole in a non-uniform external field. Then we talk about continuous charge distributions. Okay, continuous charge distribution. Under that we have three types of charge distribution: line charge distribution, surface charge distribution, and volume charge distribution. Accordingly, we define three terms: linear charge density lambda, surface charge density sigma, volume charge density rho. Okay, these are the notations. And finally, Goslow. Another important law of chapter 1, that is Goslow. Okay, first topic is dipole in a uniform external field. Here we are going to obtain a simple derivation of torque due to dipole. Torque is familiar. What is torque? Rotational force, right? So dipole will show a property of rotational force when it is kept in a uniform external field. What is the meaning of uniform external field? The field, it is an external electric field. We are applying an electric field externally and it is uniform throughout. Okay, uniform, same magnitude, same direction, like that. So let us consider the case of a dipole, a permanent dipole of dipole moment P in a uniform external field E. Okay, permanent dipole means the dipole always exists irrespective of the electric field. Okay, so this is the one of the diagram you need to consider. This is directly taken from your NCERT. So we have two charges, minus q as well as plus q. So this is dipole, minus q and plus q, separated by a distance 2a. Okay, detailed study about dipole is done in the last presentation. That is part 4 of the chapter 1. What is dipole? Pair of equal and opposite charges separated by a distance 2a. And we have defined dipole moment also. Okay, dipole moment directed from minus q to plus q. Always directed from minus q to plus q. It will give you the strength of the dipole. So when we are keeping a dipole in external electric field, see, this is our external electric field. This is the direction shown. Minus y direction to minus y direction to plus y direction of electric field. So what happens is that when an dipole is kept in this kind of electric field, it will have a tendency to move or rotate with respect to the direction of electric field. So here it is plus q is kept. So force acting on this due to this q will be in this direction, QE will be in this direction, and force acting due to minus q will be in the downward direction because of the direction of electric field, like this. Okay, the plus q always along the direction of electric field and minus q exert a force opposite to the direction of electric field. Okay, that means two equal and opposite charges. Okay, two equal and opposite charges in different line of action. So this is like this and this is like this. So it will have a tendency to rotate with respect to axis, a rotation. Okay, like this. This arrow shows the rotation. Okay, so this will create a torque. There we define the torque due to dipole. So in order to derive an expression, we will consider another diagram, another simple diagram. Okay, so this diagram you have to note down. This is the diagram we are using to do the derivation part. So this is the direction of electric field. Okay, direction of electric field. Okay, so here it is directed from this minus x direction, along x direction. So based on the direction, here it will be positive and here it will be negative, right? Positive to negative. So now see this is our dipole. Positive plus q here and minus q here. Okay, plus q and minus q. So plus q, so plus charge q, and here it is negative. So it will have an attractive force. So F will be due to plus q will be in this direction. This formula is F is equal to q into E. the relation between force and electric field intensity. That formula is used. F is equal to Q into E along the direction of electric field. Now here minus Q will have a tendency to move in this direction because here it is positive. So this part is positive. So minus Q will be in this direction. So force due to minus Q will be in the opposite direction. So these two equal and opposite charges. So we can say that this F is acting in this direction Q into E, and this force is acting in this direction minus Q into E. And this is the dipole separated by a distance 2a. Okay, these lines shows the external electric field. What is the direction of dipole moment? Minus Q to plus Q. This is the direction of dipole moment. Now based on this diagram, how the rotation occurs? The rotation will be in the clockwise direction, right? So it will have this dipole will have a tendency to rotate in the clockwise direction. Okay, clear? So the force QE due to plus Q and net force on the dipole will be 0 because net force or translational force QE plus minus QE will be 0 because electric field is uniform. However, the forces acts at different points. This term you remember? Couple. What is couple? If the force acts on a different points, equal and opposite acts on if equal and opposite forces act on a different points, it produces a couple which results in a torque. So that's why the torque is developed on the dipole. When the net force is 0, the torque is independent of this. That is, there will be a torque. Even though net force is 0, there will be a couple. Because of the couple, there will be a torque. Its magnitude is equal to the magnitude of each force multiplied by the perpendicular distance or the arm of the couple. That is the definition of torque. Torque is equal to force into perpendicular distance. So the dipole will rotate till it become parallel to the electric field. So dipole will continue rotate in a clockwise direction as I have shown in the previous slide. Okay. So these are the few points you need to write down. Now the formula for torque. Torque is equal to force into perpendicular distance. This is a formula you have already studied in your last year physics. Torque is equal to force into perpendicular distance. That formula we have to use here to obtain the expression. Back to the diagram. Okay. We have to use the formula once again. Torque is equal to force into perpendicular distance. So this is the formula, force into perpendicular distance. So this perpendicular distance is what in this diagram? So this BC is the perpendicular distance. Okay, note down, listen. This BC is the perpendicular distance. Okay, so in order to find out the expression for BC, consider this diagram. From the figures, this is angle theta and sine theta is equal to opposite side by hypotenuse. Okay, what is opposite side? BC divided by AB. Okay, BC divided by AB. So BC divided by AB. AB is the distance of dipole, that is 2A. So you can write BC is equal to 2A sine theta. Okay, this perpendicular distance expression we have to use in the formula. Now we write torque is equal to force into perpendicular distance. What is force? Magnitude of force is QE. Okay, magnitude of force only you need to consider Q into E. F is equal to Q into E multiplied by perpendicular distance BC. Now we substitute for BC. So QE into 2A sine theta. That means Q into 2A into E sine theta. Just Q and 2A we have written together. Why you have written this together? What is Q into 2A? Remember, charge into distance, Q into 2A. This is nothing but our dipole moment. So we can write it as P into E sine theta. Okay, P E sine theta. What is this formula? P E sine theta. Remember, A B sine theta, A cross B. A B sine theta is equal to A cross B. So we can write it as P cross E. So in using vector notation, torque is a vector quantity. So tau is equal to P cross E, or simply P E sine theta. P is also a vector quantity, E also a vector quantity, and tau also a vector quantity. So torque is denoted by using symbol tau that we have studied last year. Tau is equal to P cross E. So this is another important derivation. Okay, even though since small derivation, many times it is asked in the question paper, board exam paper. So tau is equal to P cross E or P E sine theta. And the direction is perpendicular to the direction of P and E, or given by right hand rule. Okay, no need to bother about direction, you just understand it is perpendicular to both P and E. Okay, so remember this formula. Some hot questions related to this torque. What is the maximum value of torque acting on dipole? Can you answer? What is the maximum value of torque? Maximum value when theta is equal to, this is sine theta, so when theta is equal to 90. So we'll get maximum value of torque when theta is equal to 90. Okay, so tau is equal to PE. That time maximum value is PE. That is, the dipole is aligned perpendicular to the direction of electric field. That is, theta is 90. Another question is, another important question always asked is, at what orientations the dipoles placed in uniform electric field will be in stable equilibrium and unstable equilibrium. These two terms, stable equilibrium and unstable equilibrium, we need to understand what it is. For that, let us consider when dipole is kept parallel to the electric field. Case 1. Dipole is kept parallel to the electric field. That means theta is equal to 0. So dipole is, electric field is in this direction, dipole is also along the same direction. In that case, theta is equal to 0. We call it as, it is in stable equilibrium. Okay, I will explain once again. This is, the answer is for stable equilibrium when theta is equal to 0. That is when dipole is kept parallel to the electric field. Second case, unstable equilibrium when dipole is kept anti-parallel to the electric field. That is at 180 degree. So in two ways, if you are keeping dipole parallel and anti-parallel, theta 0 and theta 180. So in these two cases, actually torque will be 0, right? When theta is equal to 0, tau is equal to PE sin theta, torque will be 0. But this is the position of stable equilibrium and unstable equilibrium. Okay, we will understand it. In both the cases, torque is 0, but net force is not equal to 0. There will be a net force acting on it. We will consider this diagram. First case, when E is parallel to P. Diagram 1, E is parallel to P. So this is the direction of electric field, okay, positive to negative. And this is the direction of dipole moment. Minus Q is here, plus Q is here. So dipole moment and electric field along the same direction. This is the case 1, E parallel to P. Here the net force is in the direction of electric field, increasing field. This is the direction of net force, direction of increasing field, same direction. Okay. Direction of net force, that is QE and minus QE. Direction of net force, QE will be greater than minus QE. So direction of net force will be along the direction of QE. So this direction. And direction of field also in this direction, increasing field. So this is the case of stable equilibrium. Second case, E is anti-parallel. How do we keep dipole in the second case, E anti-parallel to P? Suppose electric field is in the same direction. We have to keep the dipole just opposite of this case. That is minus Q here and plus Q here. Okay, then it will be anti-parallel. This case is called anti-parallel. Here you can see force on charge Q will be in this direction, right? Force on charge Q and force on charge minus Q will be in this direction. So direction of net force will be in the direction of decreasing field. See, direction of electric field is here in this direction. I will show. So this is the direction of electric field. Positive here and negative here. Okay, here also positive here and negative here. So here in this case you can see, in the second case you can see force on Q. This is plus Q, right? It will have a tendency to apply force on towards negative charge. So force on Q will be in this direction, and this negative Q will have a tendency to move towards positive. So in this direction, opposite direction. And the direction of net force will be in the opposite direction. This is the direction of net force, and the direction of field will be in this direction. So this case is the case of unstable equilibrium, and this case is called case of stable equilibrium. Here both are in same direction, direction of net force as well as direction of increasing field along the same direction. Because here minus Q, it will have a tendency in this direction, force will be in this direction, and plus Q, force will be in this direction. Okay. So these are the two diagrams based on the previous question. Now dipole in a non-uniform external field. What is the meaning of non-uniform external field? The fields are non-parallel. because only in uniform external field we say the fields are parallel, same magnitude, like that. If they are non-uniform, it is non-parallel, and the field magnitude also will be different. Field will be stronger at particular point and weaker at some other point. So net force will be there here. Okay, there is net force because your field is not uniform. So net force will not be equal to 0. So there is a translational motion along with rotational motion. That is an important point. In non-uniform external field, there will be translation motion also. So this is the question it will be asked. What is the behavior of dipole in non-uniform electric field? You have to answer like this. The dipole will have both rotational and translational motion. The rotational motion will stop when the dipole becomes parallel to the electric field. That is the case of similar to the previous case. But the point is here it has translational motion also. Okay. So that is all about uniform field and non-uniform field. Now we will move on to the next topic, that is continuous charge distribution. Three types of charge density we will discuss here. Okay. So what is the meaning of continuous charge distribution? See, there are several situations wherein we need to consider the charges distributed throughout the line, throughout the surface, throughout the volume, like that. So there we have to consider continuous charge distribution rather than a point charge. Okay. So a system of closely spaced charges is said to form a continuous charge distribution. That is large number of charges in a particular fashion. It is useful to consider the density of charge distribution as we do for density of solid, liquid, gas, etc. Okay, we will define density of each of these charge distribution. First one is line or linear charge density. It is denoted by lambda. Okay, this is lambda. What is linear charge distribution? If a charge is distributed over a straight line, or over the circumference of the circle. Okay, along the line, whatever it is should be along the line. Then we call it as line charge or linear charge distribution. We define its density as, density is what? So linear charge density is charge per unit length. Here it is along the line, so charge per unit length. And its SI unit is charge coulomb and length meter, coulomb per meter. So this is a situation along the line. Okay, a charge is positive charges are shown along the line. So if we consider a small amount of charge dq along the length dl, we can define charge density lambda is equal to dq by dl. Then we can find out the total charge q is equal to lambda, dq is equal to lambda into dl. That means total charge q is equal to integral lambda into dl. That is, integration is done to find out the total charge. Differentiation, opposite of the differentiation, that is integration. Now electric field intensity due to line charge distribution. Now we'll write down the expression for electric field intensity in terms of this line charge density. For that, let us consider a line charge distribution like this. This is the line charge distribution. A small differential length delta L or dl, in whatever we can consider, both way we can write. Okay, delta L is considered. Point P is at a distance r dash from this line charge distribution. Okay, then we can write electric field intensity due to this charge distribution. Okay, this charge distribution, what is electric field intensity at this point P? 1 by 4 pi epsilon naught dq by r square. That is, delta L consists of charge dq. Okay, dq by r square. Then using the charge density lambda, we can write dq is equal to lambda into dl. This formula we have written in the previous slide. We have seen lambda is equal to dq by dl, or dq is equal to lambda into dl. So we can write d is equal to, what is the meaning of dE? Electric field intensity, differential amount of electric field intensity. Because we have written dE because we are considering a small differential length delta L or dl. So we have written accordingly. Then E is equal to lambda by 4 pi epsilon naught. Sorry, lambda is written twice here, only one lambda. 1 by 4 pi epsilon naught integral lambda dl by r square. Okay, so here it is 1. Okay, not lambda. Make this correction. Second type is surface charge density sigma. If the charge is distributed over a surface area, then distribution is called surface charge distribution. Okay, surface charge density is the charge per unit area. Its unit is coulomb per meter square. Okay, we'll see the formula. So this is a surface. Along the surface, the total charge is distributed throughout the surface. Then we define surface charge density by sigma. It is given by charge by surface area, dq by ds. Okay, dq by ds. Or we can write q is equal to integral sigma into ds. Okay. So in order to find out the electric field intensity, consider a sheet of charge distribution and take a small differential area element delta S. Then electric field intensity at P due to this surface element is given by D is equal to 1 by 4 pi epsilon naught dq by r square. We are just using the formula of electric field intensity here. Okay, no need to confuse. And just substituting for dq in terms of charge density. dq we have to substitute as sigma into ds. That's all. Same formula just in terms of charge densities. So then to find E, you have to find the integration. E is equal to 1 by 4 pi epsilon naught integral sigma ds by r square. All these you just need to remember. Okay. This volume charge density. If the charge is distributed over a volume, we call it as volume charge distribution. And its definition is charge per unit volume. Okay. SI unit is coulomb per meter cube. So this is the volume charge distribution. Okay, charge is dq and volume is denoted by dv. So notation for volume charge density rho is equal to dq by dv or delta q by delta v. Okay, delta and d, no need to worry. We can write dq by dv. For this limiting case, all delta are replaced by d. So dq by dv. And for finding electric field intensity, let us consider a volume. And here a small differential volume element delta V is considered. Okay, where delta then charge on this volume is equal to delta Q is equal to rho into delta V. And in the formula I have written in terms of dq and dv. Okay, not delta. So d is equal to 1 by 4 pi epsilon naught dq by r square. Small charge dq, small electric field de. Differential, d means differential element, differential electric field. Then 1 by 4 pi epsilon naught. For dq you substitute as rho into dv. Then finally E is equal to 1 by 4 pi epsilon naught integral rho dv by r square. Okay. So these are the three types of charge distribution. It's clear, no? Line charge, surface charge and volume charge. No need to confuse. Now next is Goslow. Before Goslow, let us revise the electric flux once again because we will be using electric flux in Goslow. So what is electric flux? Already we have seen this definition, right? If you are considering a closed surface, electric flux linked with a small surface element delta S is given by delta phi is equal to E dot delta S. Okay? Or E delta S cos theta. And total electric flux is given by phi is equal to summation. This will replace as integration. Okay, the summation is replaced by integration. So this is the formula for our electric flux in terms of E and delta S. Okay, that phi is equal to integral E dot ds. So remember this formula of delta phi, that is electric flux in terms of electric field intensity. This is the formula we often use. Remember this formula, okay? Goslow, very important theorem, okay? Goslow. Gauss theorem states that the total electric flux over a closed surface, okay, closed surface enclosing a charge is equal to 1 divided by epsilon naught times the net charge enclosed. Okay, this is a statement. You have to study the statement as such. So here we have to consider a closed surface, spherical surface. A closed surface means a closed, totally closed sphere. For example, a spherical surface. On that a small surface element delta S is considered. Okay, a charge Q is there inside this surface. A charge Q is kept at the center. Then in order to find the total electric flux over this closed surface by Gauss law, it is given by 1 by epsilon naught times the net charge enclosed. Okay. Okay, this is the case. Mathematically, Gauss law is given by total electric flux, that is phi is equal to, we have written this formula, phi is equal to integral E dot ds, right? So phi is equal to integral E dot ds is equal to 1 by epsilon times the charge enclosed. What is the meaning of charge enclosed? See, this is our spherical surface, closed surface. How much charge is there inside this Q? Okay, in this particular example, one charge Q is kept here. It's not necessary that you should keep the charge at the center itself. Okay, anywhere you can keep the charge, but it should enclose. The closed surface should enclose this charge. So in that case, total flux is given by, this is the formula for total electric flux in terms of electric field intensity, that is given by Q by epsilon naught. Okay, Q by epsilon naught. This is the formula for our Goslow. Very important theorem. Okay, phi is equal to Q divided by epsilon naught. What is the Q? Q is the total charge enclosed by the closed surface, and phi is the total flux. Now illustration of Goslow. So consider a sphere of radius r which encloses a charge Q at its center. The same example, same case. Let us take a flux associated with small area element delta S as shown. Okay, small delta S element we have considered, and we have to find out the flux associated with it first. The area element delta S, okay, delta S and R, the direction of electric field along the same direction, radial. Okay, direction of delta S normal outward, electric field intensity also radial outward, same direction. Okay, they have the same direction, delta S and electric field intensity vector R. So formula for delta phi is equal to E dot delta S. E is equal to Q by 4 pi epsilon naught R square into R cap in the vector form of electric field intensity dot delta S. Since these two are in the same direction, that dot product will be same. So delta phi is equal to Q by 4 pi epsilon naught R square into delta S. Okay, this is the dot product of these two will be just delta S because same direction. Then the total electric flux through the sphere is obtained by adding up the flux through all different area elements, because we have just considered a small differential element delta S. Like the total flux we need to consider. Okay, this is the flux associated with that small element delta S. So total flux we need to find out. For that, summation of all these delta S's. Okay, summation of all these delta S's. Or phi is equal to Q by 4 pi epsilon naught R square summation all delta S into delta S. Summation of all delta S you will get, what will you get? The surface area of that sphere, that is denoted by S. Okay, summing all delta S, small differential elements. When you add, summation means add all these small delta S elements, you will get total surface area, that is S. Where S is the total surface area of the sphere, which is equal to 4 pi r square. This is the formula for surface area of the sphere. Okay, substituting that, you will get phi is equal to Q by 4 pi epsilon naught r square into 4 pi r square. That is equal to Q by epsilon naught. So this is the illustration or the derivation of Gauss theorem. Okay, Goslow. So phi is equal to Q by epsilon naught. So here we have considered a sphere, spherical surface, a closed surface. Charge Q is enclosed by the surface. Then net flux, total flux will be, total flux through the sphere is given by Q by epsilon naught. This is nothing but our Goslow statement of Goslow. Now some significance of Goslow. The total electric flux through the closed surface is equal to 0 if there is no charge enclosed by the surface. Just opposite of the statement. We said by Gauss law, total electric flux will be equal to net charge 1 by epsilon naught times the net charge enclosed. If there is no charge enclosed in the closed surface, what will be total flux? 0. It is true for any closed surface, no matter its shape. Okay, it should be closed surface. So it is a very important point of the Gauss law, because Gauss law is applicable only to the closed surface. Okay, only to the closed surface. An imaginary surface enclosing a charge is called Gaussian surface. We use this term often. Okay, in application of Gauss law, you will understand it more clearly. If you are considering any closed surface, any charge, if you want to apply Gauss law, we have to consider a closed surface enclosing that charge, and that closed surface is called Gaussian surface. It can be of any shape, but it should be enclosed. It should be a closed surface. The term Q on the right hand side includes all charges enclosed by the Gaussian surface. Okay, Gaussian surface means closed surface, so charge should be enclosed. Gauss law is often useful towards such easier calculation of the electrostatic field when the system has some symmetry. See, electric field intensity we can find out using the formula for electric field intensity, 1 by 4 pi epsilon naught Q by R square. But there are certain situations we have different kind of charge distribution, different symmetry. In that case, we have to use Gauss theorem only, and we will substitute. We use the Gauss theorem, Gaussian surface and Gauss theorem. It is also based on a inverse square dependence, inverse square law, just like our Coulomb's law. Okay, so these are the important points of Goslow. Okay, Goslow is another important theorem of chapter 1, just like Coulomb's law. Both the theorems you have to understand properly, and next part of this chapter I will be discussing about the application of Goslow. Some 3-4 applications you need to learn that you will understand in detail. Okay, dears, thank you. So few hot question also there along with this that you have to answer. I have not given the answers. Just try these hot questions. Question 1 and